Welcome to the Explainer. You've probably seen a chatbot do something that seems, well, impossible. Write a poem, answer a super complex question, even spit out working code. It really feels like magic, right? But it's not. Today, we're going to pull back that curtain and see exactly how large language models actually work, right from the ground up.
See, what's really going on under the hood is just a super sophisticated game of prediction. The model is just guessing what word or piece of a word should come next over and over again. It's all based on the insane amount of patterns it's learned from the data it was trained on. So it's not thinking in the way we do. Nope, it's just calculating probability.
All right, so how does it actually do that? Let's get into it. We're going to peel back the layers on this whole thing, starting with the most basic building block you can imagine. Okay, so at the very core of every single large language model, you'll find something called a neural network. Really, you can just think of this as the learning engine. It's what takes in all that data and powers the whole operation. So what's a neural network made of? Well, it's made of neurons. And you can think of a single neuron as a tiny little calculator. Super simple. It just takes in some numbers, multiplies them by these things called weights, which, are really just more numbers, and then it passes the result on to the next neuron. Now, imagine not one of these, but millions or even billions, all connected together in layers, each one doing its tiny little piece of math. But here's the thing. When you first set one of these networks up, all those weights are basically random. It's like having a giant machine with millions of dials, all set to completely random positions. So naturally, if you put something in, you get total gibberish out. The entire goal of training is to figure out how to tune every single one of those dials just right. Okay, but how does it know how to tune those dials? Well, that's where training comes in. You showed the network millions and millions of examples, and for each one, you use something called a loss function to basically tell it, hey, you got this wrong, and here's how wrong you were. This loss is just a single number that measures the error, and the whole game is to get that number as close to zero as you possibly can. And it does this with a really cool two-step dance that just repeats over and over. First, there's a process called backpropagation. Its job is to go backwards through the whole network and figure out which of those little dials, which weights, were most responsible for the mistake. It literally assigns the blame. Then, once it knows who to blame, another process called gradient descent comes in and just nudges those dials, those weights, just a tiny, tiny bit in the right direction. The idea is next time the error will be a little smaller. Okay, so we've got this incredible learning engine, but there's one giant problem. It doesn't understand words. It doesn't speak English or Spanish or Japanese. It only speaks one language, math. So we've got to figure out how to translate our words into numbers it can actually work with. And the first thing we do is chop up our text into pieces. These pieces are called tokens. Now, a token might be a whole word, like cat, or just part of a word, or even a simple comma. This process takes our messy, flowing language and turns it into a nice, neat list that a computer can start to make sense of. Right, so take a word like unbelievable. Instead of being one big, clunky token, it might get broken down into three: un, believe, enable. This is actually really clever because now the model can learn the meaning of prefixes and suffixes. It's a trick that lets it handle a massive vocabulary and even figure out words it's never, ever seen before. So once we have these tokens, each one gets converted into a long list of numbers. We call this list an embedding, or a vector. The best way to think about it is like a coordinate in a massive multidimensional space, a giant map of meaning. And what's so cool is that through all that training, tokens with similar meanings, like, say, king and queen, or walking and running, end up with coordinates that are really close to each other on this map. All right, let's recap. We've got our learning engine, the neural network, and we have a way to turn our language into numbers it can understand. So now, what do we actually do with all this? Well, we point this entire massive system at one single, almost ridiculously simple goal. And here it is. At its core, an LLM is trained to do one thing and one thing only: predict the very next token. That's it. That is the whole game. All that complexity, all that computing power, all that money, it's all spent just to get incredibly good at answering one simple question. Given the string of text, what's the most likely thing to come next? This is the perfect example, right? If you give the model the phrase peanut butter and, it doesn't know about sandwiches or food. It has no idea. What it does know from seeing it billions of times in its training data is that the token jelly has a super high probability of being the next one. And the token for wrench, the probability is practically zero. It's all just statistics. But wait a minute. Just predicting the next word isn't always that simple. You need context, right? You can't just look at the last word in a sentence to know what comes next. And this was a huge problem for a long time, until a revolutionary new architecture called the transformer came along and completely changed the game.
So, you see, older models had to process text sequentially, one token at a time in order, just like how we read. This made them really slow, and they were terrible at remembering things from the beginning of a long sentence by the time they got to the end. But transformers, they're different. They can look at all the tokens in the input at the exact same time. This parallel processing means they can see how every single word relates to every other word, no matter how far apart they are. And the secret sauce that makes this possible is a mechanism called attention. This is the absolute key. You can think of it like this. When the model is about to predict the next word, attention allows it to look back at all the previous words and decide which ones are the most important to pay attention to right now. It's like it's highlighting the most relevant parts of the text to help it make a better guess.
And this sentence is a fantastic demonstration of why that's so important. The trophy doesn't fit in the suitcase because it is too small. What does it refer to? The trophy or the suitcase? For a human, it's obvious, but for a computer, it's tricky. The attention mechanism can correctly calculate that the word it is most strongly linked to suitcase, not trophy. It's this ability to connect the dots that gives these models their power.
So when it's time to actually generate a response, which is called inference, the model isn't learning anymore. All those weights are locked in place. All it does is run this simple little loop over and over and over. Step 1, it looks at the input and predicts the probabilities for every possible next token. Step 2, it picks one. Step 3, it sticks that new token onto the end of the input. And then it just repeats the whole process, using that slightly longer text as the new input. That's how it builds an entire paragraph, one single token at a time. Okay, we're almost there. We're at the final, and honestly, maybe the most crucial piece of this entire puzzle. Understanding this one concept is the key to understanding why LLMs sometimes act so strangely and where their real-world limits are. Here's the deal. An LLM doesn't have infinite memory. It can't see the whole internet. It can't even remember your entire conversation if it gets long enough. At any given moment, it can only see a fixed number of tokens. This limit is called the context window, and it's basically the model's working memory. It's short-term memory. And this single limitation explains so many of the weird things these models do. It's why a chatbot might completely forget what you were talking about at the start of a long conversation. The early parts have literally fallen out of its memory window. It's why you can't just feed it a giant document and expect it to know everything in it. If it doesn't fit in the window, to the model, it doesn't exist. So this memory limit really does change everything. Once you grasp the idea of the context window, so much about why some prompts work and others fail just clicks into place. But what do we do about it? How do we work around this fundamental limitation? Well, that's exactly what we're going to break down in the next explainer.